So we're going to finish up 9.2, part 2. And this is where we're going to start to look at some of the graphs we can do in polar form on the calculator, and also converting between polar and parametric, function and parametric, converting between everything, okay, all the different formats. So remember, when we write a point in polar, what you're given is an r value and a theta value. So r is the distance from the origin, either right or left, and theta is an amount of rotation, clockwise or counterclockwise. So let's graph r equals 2. Okay, this is a polar graph. The way you can graph this is the same way you'd graph anything. Let's find some points and then draw from there. Can somebody give me a coordinate? It has to be in this format, but it has to be on the graph of that shape. What would be a coordinate that you could plug into that equation and it would work? Yeah?
2, 0.
All right, so 2, 0 is 1 point. There's 1 point on your graph. What's another point?
2, 180.
Okay, so 2, 180. I'm just going to graph some points and see if we can figure it out. So 2, 180. Okay, there's another point on your graph. What else? Yep.
290.
So we can do 290. 290. Okay, there's another point on your graph.
245.
245. So that would be right there. What's another one?
135.
Okay, so 2, 135. It's over here.
It's just 2 any degree.
2, we could do negatives. Nobody was saying negative, but you could do 2, negative 90. That would bring you down here. So it's 2, comma, any angle, which basically means the shape is what? It's a circle. And that's what polar is built for doing, drawing circles. It's a circle. What's that?
That's a pretty good circle.
Yep, that's my circle. So now, if we want to put that in on the calculator, well, what we have to do is go to mode, put it in polar, and it's going to say r equals. So we could put in r equals 2. And now we have to make sure that we go through all the possible thetas. Theta is like our parameter. All these things you guys were giving me that was changing, that's called a parameter, just like t in parametric. What are all the different angles you would have to go through so you had every single dot on the circle?
0 to 360.
You'd have to go from 0 to 360. And what would be a good stepping amount for theta?
1.
Yeah, 1. That's going to graph 361 points. As far as your window, negative 10 to 10 is fine. But if you do negative 10 to 10 on both the x and the y, remember it will distort your picture because your screen is not a square, it's a rectangle. So it's going to look more like an ellipse. But if you do zoom 5, that will set the screen so that it looks proportional. In fact, there's a quick way you can make any screen look proportional if we just look at the ratio of the length to width on the zoom. So a perfectly square window that's proportional has basically a ratio of, if you take the x and divide by the y, of about 1.6. So if you make your x value 1.6 times your y value, you'll roughly get a window that shows you objects not being distorted. The x should be 1.6 as big as the y. All right. And what would happen, let me zoom in and see if I can still see it. Zooming in will still keep it proportional. It'll just zoom it in. Yep, looks good. Nice, smooth circle. What would happen if I went 0 to, say, 270 for my parameter?
Spot missing.
Yeah, I only go to 3. I only go 3/4 of the way around. And what would happen if I set my t step to 20? Or, I'm sorry, theta step.
You'll have less points.
I'm going to have less points. I'm going to get 0, and I'm going to count by 20s, so it's going to graph real fast. But the edges might start to look more like a 21-sided polygon. Not bad, but I can definitely start to see the edges looking a little straighter than they were before. Okay, so that's how you graph R equals. Let's graph theta equals. So this is the equivalent of like we just did y equals, and you can do that one on the calculator. Now it's like we're doing x equals. You can't do that one on the calculator because the calculator can only get one variable by itself, and in y equals notation, like function notation, it's 1. In polar notation, it's r. So we're going to have to do this by hand. All right, so that's 2 radians, which just to get an idea of what that is, that's 2 times 180 divided by pi. So it's about 114.6 degrees. That's easier for me to graph than 2 radians. Okay. What's a point that would be on the graph of theta equals 2?
One comma 114.6 degrees.
So 1 comma 114.6. So that means you'd go right 1. And then 114.6, huh? A little after 9. Okay. What's another one?
2 comma 114.7.
So 2, all right, we know what the angle is, 114.6. Put me right about there. What's another one?
3 comma 114.6.
Okay, another one?
4 comma 114.6.
-1.
-1. For your angle? Or no, for your radius? Yeah, you could have 0. And what's another one?
-1.
So -1.
-1, 65.4, is that it? No, wait.
-1, 14.1, 114.6.
Yep, -1, 114.6. And then if you did like -2, right, you could keep going, but the idea is what shape are we getting here?
A line.
We're getting a line.
Wow. It's a line.
So if you want to draw a line through the origin, that's not that hard to do. You just have to say theta equals, and then you put your line. Now, if you wanted to draw a line that had a certain slope and a certain y-intercept, that's a little bit hard. And we might have talked a little about this. But what did we say yesterday? What's our formula for y?
Y equals, what do you mean?
For the y, though, when we write it in polar.
R sine theta.
So r sine theta. And what's the formula for x?
R cosine theta.
R cosine theta. And if we wanted to graph this on the calculator, what letter needs to be by itself? R. So bring all the r's to the same side. So r sine theta minus mr cosine theta equals b. And what can we do with these two terms on the left? We're trying to get r by itself.
Defined by R.
No,
Uh,
can you like inverse?
Well, we got to be careful. In case r was 0, we could have a radius of 0. We don't want to divide by 0. But what else can we do with the r? Somehow we've got to get r equals on the left side.
You can't do like inverse cosine or sine.
No, we don't want to do any inverse trade because you'd have to do it to every term, and that would get kind of messy. We're not trying to isolate theta. We're trying to isolate r.
Divide by cosine theta and divide by sine to get rid of the thing.
Well, if you divide by sine, remember you got to do it here, here, and here.
Oh.
So then you're going to end up with cosine over sine, which I guess you could change to cotangent, but that's still not going to help you to isolate r. What else could we do on the left-hand side with the r? We can't subtract it because it's not being added. There's no r plus.
Could you like turn it into the number it's supposed to be? Like r multiplies sine theta, right? Could you like do it out or something?
Think about how you would have gotten to this step. Like if you had a step before this step.
Factor it out.
Factor it out. That r has been distributed to each term. So what we want to do is get rid of having that distributed, and then we can only write the r one time. So we'd have r sine theta minus m cosine theta. And now how could we get r by itself?
Now we can divide by sine theta minus m.
Yeah, divide by sine theta minus m cosine theta. So this is how you would write the equation of a line in polar. That's what a line looks like. So now we could pick, anything you want for your y-intercept and your slope. Just fill them in for the m and the b. So if you want to draw a line that has a y-intercept of, 4, and you want it to have a slope of 2. All right, so let's do sine theta minus 2 cosine theta. That should look like a line with a y-intercept of 4 and a slope of 2. Might have to zoom out. Right, so it does have a y-intercept at 4. The reason it might not be showing the whole line is I think I might have to set my Tmax higher. I'm guessing. Let's just try that. Oh, I'm also stepping by 20. Well, let's change that first. Let's step by 1. And you'll notice when it draws it, it starts drawing one way, and then, so it's drawing down, and then it goes back up. It's just that's the way polar works. But there's your line with a slope of 2 and a y-intercept of 4. So very complicated to draw a line in polar. I mean, relatively, compared to y equals mx plus b. Okay, so the next shape we're going to look at is not a line, not a circle. It's a different shape we've never looked at before. So we're going to graph this. 3 plus 3 sine theta. And we're going to graph it over a parameter from 0 to 2 pi because that's going to give us one full cycle. If you go beyond 2 pi, you're going to be tracing over the same graph. Let's think about what our radius is going to be between here. We've kind of done this thing before. Think of sine. What's the biggest value that would ever come out of this box? 1. And what's the smallest value? So now, if you consider it as that box, let's think of it that way. What's the biggest value that would come out of it? And the smallest would be a -3. So now I want to think about what would come out of this entire thing.
The smallest is 0 and the biggest is 6.
The smallest would be 0 and the biggest would be 6. So we're going to be drawing a shape that the distance from the origin is always between 0 and 6 units. It's not fixed though. If it was fixed, that's a circle. It's going to be changing. So the way it's going to change, we're going to analyze it in pieces. This is the graph of sine. And there's really 4 key sections we want to look at here. The first section is from here to here. The next section we're going to look at is from here to here. Then we're going to look at what's happening from there to there. And then we'll finish up with the section in black. So I'm going to break down what's happening in my problem into like 4 littler problems that I can think about easier. Okay, step by step. So let's start with the red section. The red section is going to represent angles between what and what. We're going to be plugging in for theta.
90.
0 and what? 90, or in this case, pi over 2. So let's think about what happens to the sine function between 0 and pi over 2. Then we can think about what happens to our entire thing. So it's like we're going to look at this part first, and then we'll look at what happens when we triple it and add 3. Let's start with sine. If you go from 0 to pi over 2, what happens to your sine value in the red section? It goes from what to what? 0 to 1. It goes from 0 to 1. So we know this part is going from 0 to 1. And if you triple that, you'd be going from what?
0 to 2.
You'd be going from 0
To 6.
To 3.
to what?
Maybe 6, because you got the sine can get 1.
Yep, so
Plus
let's just think about what's happening here again. This is 0 to 1. So the biggest that we could ever get for the radius here would be what?
1. Oh, wait, for the whole entire thing?
For this whole thing, what's the biggest number you could ever get? Right. If this was 1, 1 times 3 is 3, and 3 plus 3 is 6. That's the biggest radius. Now, I want to think about, I usually do the smallest one first, but someone said 6. So we'll go with the biggest is 6. What's the smallest radius you could ever get? 3. So if this was 0, times 3 is 0, plus 3 is 3. So in the section from 0 to 90 degrees, as you sketch this, so basically as you sketch it in quadrant 1, your radius is going to grow from 3 to 6. Let's see what that would look like. So at 0 degrees, it has a radius of 3. At 90 degrees, it has a radius of 6. And it's growing as you rotate. So think of it like this. The further you rotate, the more and more the radius is growing. So my lines start getting longer and longer as I rotate. Any question on that idea? So it's going to look something like this. Kind of. It's as good as I can go. Okay, so it's kind of like fanning out. The radius is growing the entire time. Now we want to look at what's happening in the next section. Okay, it's like quadrant 2. What's happening to your sine function from pi over 2 to pi? It's going from 1 to 0. So now if the sine function is going from 1 to 0, what would this entire thing be doing? It's going from 6 back to 3. Because the biggest number you're going to get in this section is a 1, times 3 plus 3 is 6. And then the smallest one you're going to get when you're all the way at 180, that's going to be 0. 0 times 3 is 0, plus 3 is 3. So the radius is shrinking back to what it was, and it does it in a symmetrical way that it did it in quadrant 1. So it's going to be like a mirror image of the way it grew, the way it's going to shrink. So I'm just going to take this, flip it Well, I'll make a copy of it first. Then I'll flip it. It's about. I don't think my tick marks are spaced perfect. That's okay. So that's what's happening in quadrant 2. What's happening to the sine function on the blue part? The values of sine are going from what to what?
0.
0 to negative 1.
0 to negative 1. So we know this part is going from 0 to negative 1. If you let sine be 0, what would you get for a radius? 3. What if you let sine be negative 1? 0. So what's happening in this part is it's shrinking. The radius is going from 3 all the way to 0 as you rotate around. So where am I going to end up here? End up at the origin. So as I start to rotate, it's going to shrink right into the origin. So it's going to kind of do something like this. As we rotate, these are going to keep getting shorter and shorter and shorter until finally we get all the way around. So it's going to shrink and go right into the origin. And the other part is going to look symmetrical, except it's going to be growing from 0 to 3. So that's going to look something like, and then flip it. Oh, my tick marks are not. I guess I'll just draw it by hand. I don't think I drew this graph evenly. Oh, well, that's the general idea. It should look symmetrical. And does anyone see what that kind of looks like? Yeah, it kind of looks like a heart if you.
I guess so.
It looks exactly like a heart. And it does. It's perfect. Look at it. Especially if you rotate it. See? Look at that.
Nice.
I mean, that doesn't get any better, right? It looks just like a heart. So because that looks identical to a heart, we call that shape a cardioid. Due to its almost exact heart-like appearance.
We can just plot a heart.
So when you have a cardioid, you can change the amount that it comes in on itself. So like some cardioids, this might be more of a curve in, depending on how you change the numbers, or it might look a little bit smoother. Might not dip in as much. It all depends on how you change the numbers. But a cardioid generally has this formula. A number, plus or minus the same number, and then sine or cosine. The number can't be a 0. Anything besides a 0. So if you go back and look at our problem, a was equal to 3. It was 3 plus 3 sine. That is a cardioid.
Why do they have to be the same number?
Well, if they're not the same number, I don't remember what you call it, but it's not a cardioid. So let's graph 3 plus 3 sine. Let's make sure we're at 0 to 360. That's fine. All right, let's hit graph. This one looks a little rounder than I drew it, but still the same kind of idea. Okay, but there's.
How does that look anything like a heart?
It looks exactly like a heart.
Dang. Who named this?
So,
Something like a heart.
if you if you do zoom 6, that's going to distort it. I think that makes it wider.
Wow.
But if I made it taller, it would probably look more like a heart.
Can you draw with a big tip?
How would we make it taller? Do we want to make? What do you want to do? Maybe make the x.
X value is smaller.
If we make the x value smaller, let's see. Does that make it look taller?
That is the one.
So yeah, that would eventually do it, but I go off the screen now.
You hit.
That's you hit the
That's your
line.
Y-max.
Oh, I hit the Y-max.
That's right.
I actually think that did it. That's what I was trying to do. So that looks a little more like a heart. But the idea, yeah, it looks exactly like a heart.
None of these look like a heart.
Yeah, it's a heart. Look closer. Put glasses on. It's a heart. So that's a cardioid. Now, if you change the numbers so they are not equal, let me zoom back out. It's too small to see. Let me zoom back in. That's going to go off the screen. I just need to set Y-max a little higher.
That's
That's
Hager,
it.
that's X.
No, that's what I said. I said Y-max. Why did you press the wrong one? Stop it. Fooling around now.
That's
Y-max. See, I said to press Y-max, right?
Yeah.
So there's our cardioid. Now, if you change it so the numbers aren't equal, like let's do like a 7 and a 3. What's this one do? So it's not really like an ellipse. It still has kind of a flatter part on the bottom, but it changed it so it doesn't really have that indentation, right, going in. Now let's flip it around the other way. Let's make this a 3, make that a 7. I think what this is going to do is it's going to make it loop on itself. It's going to go in so much that it crosses over itself, I think. Yeah. So now it's even more. But that's not a cardioid. Okay, that's something different. Now, what do you think would happen if we change, we can leave it like that. If you change sine to cosine.
I don't know.
What's the connection between sine and cosine when you graph them?
Sine y, cosine x.
Okay, so not in terms of like a unit circle, but I mean in terms of a transformation. Like if you graph sine and you graph cosine.
They're inverse. Or like they go opposite. Oh,
How would you transform one into the other? Yeah?
Shift 90 degrees.
Shift 90 degrees. So if sine and cosine are off by 90 degrees, how do you think that's going to translate to a graph in polar?
putting it sideways.
It's going to rotate at 90 degrees, exactly. So if I do, so see how it looks now, I'll just save that. And now change sine to cosine. You're going to get a 90 degree shift, which in polar causes a rotation. There you go. So it should have stayed the same size, but now it's just rotated 90 degrees. So that's the difference between sine and cosine. And if we had kept the two numbers the same instead of changing them, you would have seen it with a cardioid as well.
What about tangent?
We don't really graph anything with tangent. You could try it and see what happens. But remember, the problem with tangent is you have undefined values, so something weird's going to happen. It's probably going to break or go off the screen. I don't know. Remember, you only have to go from 0 to 2 pi to get a full picture. If I do this, 0 to 720, what's happening?
It's gonna trace itself again.
It's going to trace itself twice. Now, if you step by 7.5s, I don't know, I'd have to think about that, I'm not sure. But if you step by 10s and you trace over yourself, are you going to end up stepping in the same spots you did before? Yeah, you're going to end up in the same spots. Now, let's say you step by like 17s. As you count from 0 to 720 by 17, do you think you end up stepping in the same spots the second time around?
Oh no.
No, because you're not going to end at 360 with 17. So what's going to happen here is it's probably going to make it look bolder because you're going to be a little bit off every time. See what I mean? It looked bolder because it wasn't exactly tracing it, and it's starting to look a little rough. Not as smooth. Okay, so that's a cardioid. And now let's look at how we could take an equation like a cardioid and change it into function notation. Not saying we're going to be able to graph it, because we have to be able to get y by itself, and I don't think we're going to be able to do that. But graphing here is not the goal. The goal, when you're changing from polar to rectangular, is to get rid of your r's and thetas and turn them into x's and y's. These are all the formulas we've learned this week that can take and give you some kind of relationship between x's, y's, r's, and thetas. That's all four of them. So what we do is we use substitution. Okay, we substitute in, and we try to get rid of all the r's and thetas. Let's try it with a cardioid. So 3 plus 3 sine theta. What's something in this formula, we'll start on the right side, that we do not want there if we're trying to make this rectangular?
The theta.
Yeah, the theta, and what's that part of?
The sine.
It's part of sine. So using what's up above, does anybody see what sine theta would equal?
It equals y over r.
It equals y over r. Yep. Sine of theta is y over r. So that's a formula we learned yesterday. Let's substitute that in. So now it's kind of in between. It's not polar anymore because you don't have a theta, but it's not rectangular either because now you're putting r's and y's together. So it's in between. Yep. Oh yeah. Yeah. Okay, so we got rid of the sign. I like that, but now we introduced a fraction. How can I clear this fraction?
Multiply by the multiply by r on both sides.
Multiply by r on both sides. Yeah. So if you multiply everything by r, what's that going to give me?
It's going to equal r squared equals 3 plus 3y.
3r
Oh, because you have to multiply every term by r.
plus
3y.
3y. Okay, so that's a little bit better because at least we don't have a fraction there. Now, what's something else that I could get rid of here that you see up here?
R squared equals x squared plus y squared.
So we can get rid of r squared. We know that's x squared plus y squared. So then, if we know r squared, we should know r too. What is r?
X plus y. No, the square root of x squared plus y squared.
Right. So that's r, and then plus 3y. Now you can't isolate, at least I don't know how to isolate y there. So we're not going to be able to graph a cardioid using y equals formula. But that is the rectangular form of a cardioid. It doesn't have any r's and thetas. It has all x's and y's. So that's how you change polar to rectangular. And sometimes if the equation is simple enough, you get something you could actually get y by itself and now type it in on the calculator. But that you wouldn't be able to. You just have y's in too many spots to be able to isolate it. So any question on how we changed cardioid in polar to rectangular? So we didn't use every formula. We didn't use the cosine one because that wasn't involved this time. It could be, depending on the cardioid. You could have a cosine. And we didn't use the inverse tangent. We didn't need that. But those are the 4 formulas that you are allowed to use. Yeah?
Oh, so we didn't find like x specifically. We just kind of found x squared plus y squared as an expression.
Yeah, that was from yesterday. That's the Pythagorean theorem to solve R.
Okay.
Based on the x and the y, like the base and the height.
Okay.
So all these formulas come from yesterday. 2 of them we use when we're converting to polar. 2 of them they use when we're converting to rectangular. Okay, so we've done function to parametric. That's where you let x equal t and then replace all your variables in the other equation with t. We've done parametric to function. That's where you eliminate the parameter. we've done the one we just did, polar to rectangular. Now we're going to do polar to parametric. All right, so when we have something in polar, we could have some type of curve like that. Oh, I didn't want to move that part. Oh. So we have some type of curve. Doesn't matter what it is. Say that these are the coordinates of the point. Bless you. On that curve. Let's focus just on that one point. If we can change this one point from polar to parametric, then we can change the whole curve from polar to parametric, one point at a time. In polar, what are the two things that you would know?
The radius and
Okay.
the angle.
You would know the distance from there to there. Okay, that would be like your radius. And what else would you know?
The angle.
You would know your angle. Now, normally I would write my angle as theta, but we're going to be trying to convert to parametric. What's the variable they use in parametric? T. So let's just call it T, because that's eventually what we need to call it. So T. How many equations do you need to write something in parametric? Two. One equation is for the what?
The x.
X, and the other equation?
The y.
The y. So what we need to do is, instead of thinking about this point as a distance from the origin and an angle of rotation, we need to think about how far over did we go, and then how far up did we go. So we're going to make a triangle out of this. Let's draw. That looks pretty straight, like that. So now the side that I have colored in purple, that would be my which value?
That would be your x.
That's my x value for this particular point. And then that, from here to here, is my y. Now, if this was a circle, then this value that I just traced in red would always be what? This would always be the same, right? This was a circle, because that would be a radius, and that would never change. In this problem, it changes. We don't know what that radius is going to be. And this time it's here, another time it's right there. That's shorter. Another time it's going to be there. So the radius is going to constantly be changing. How do we know what the radius is? Well, when you have an equation in polar, that's exactly what they give you. They give you a formula to find the radius. It's r equals, and then you've got an equation. So don't label this as a fixed value. It's not fixed, it's going to change. It's going to be r, but r is calculated with what formula?
R equals f.
F of t. That's how you calculate the hypotenuse in this triangle. It uses the formula that they give you, and that's how we can account for getting different points all over the place. It's just a different radial length from the origin, which is given by the formula, and a different angle, which again, the angle is just a parameter that has to go from 0 to 360 all the time. It has to go through every possible value. So let's think about what x and y would be. Actually, we can start a little more basic. What trig function would I use if I want to find x? Well, we would use r cosine theta, but r in this case is equal to what? F of t. So it's going to be not a fixed value for your radius. You're going to have to calculate your radius each time. So r cosine t, r, right? And what would be what's the formula we learned for y?
Y equals this. It was probably that. The formula was
Was it f of t sine theta?
Yeah, it was like what we did before when we did circles. It was r sine theta. Well, this is going to be f of t sine theta. And if you're not sure why we're using cosine to get x, it's because x is adjacent. And the reason we're using sine to get y is because sine is opposite. So these are the two equations that you use when you want to convert something from polar to parametric. You're going to take what they give you in polar for your formula. You're going to put the formula in front of both. And then next to this one, you're going to multiply by cosine. That gives you the horizontal. And next to the bottom one, you multiply by sine. And that gives you the vertical. Hey, it's the same thing I wrote right here. Yeah, same thing. So remember, when they give you the formula in polar, they are going to use theta, because theta is what you use in polar. When we convert to parametric, you need to change all your thetas to t's. It's just renaming because that's the variable we use. So your function renamed with a t times cosine, and then your function renamed with a t times sine. Let's try. So here's our function. So remember, function renamed with a t times cosine, function renamed with a t times sine. So anyone have an idea what I'm going to put?
f of 2 f 7. F of radius 10.
So what's my function renamed with a t?
7 sine 2 t.
7 sine 2t. Now that is this. I don't want that. I want that. So I have to take that and multiply by what?
Cosine t.
Cosine t. So that's my radius. When you multiply by the cosine, it gives you the horizontal. Now, what about my y?
It would be 7 sine t. Or 2. 7 sine 2 t.
Okay, so 7 sine 2t. Again, if you calculate what that is, that's going to be your hypotenuse. But I don't want the hypotenuse, I want the height. So what do I do with the hypotenuse to convert it into the height of the triangle?
By sine of t.
You multiply it by the sine of t. And that's how you convert something from polar to parametric. You just take what you have, rename it to t, and multiply by cosine and sine. Let's try it. So what mode am I in? Whatever mode I'm in, I'll do that first. Okay, I'm in polar. So let's type in 7 sine 2 theta. Okay, what does my parameter have to go from?
This is 0. Two times 14. Does it have to be your max radius?
So remember, theta, or I'm in polar, so yeah, we're doing 7 sine 2 theta. What does theta have to go from to get a full picture?
0 to 360.
So normally it would be 0 to 360, but this 2 changes the period. So the period is 2 pi over 2, which is what?
0.
0 to 180. I think we're going to get a full picture if we go 0 to 180. If we don't, we'll change it 0 to 360. I don't know. We might have to do 0 to 360. I'm not sure. Let's step by ones. And let's see what we get. I know we're going to get 2. I'm just not sure if we're going to get all 4. No, I do need to go 0 to 360. I guess 0 to 360, that's the way I just need to keep it. And there's the shape, goes a little off the screen, but that's not bad. That's the shape that I get when I graph 7 sine 2 theta. So that was polar. Now let's type it in parametric and see if we get the same shape. Okay, what am I typing in for x in parametric?
7
2t, yep,
cosine t.
times cosine t. And y?
7 2t times sine t.
7 sine 2t times sine t. Let's check our window. What should my parameter go from here?
0 to 360.
We should do 0 to 360. We saw that last time. And the t step, I think 1 is good. Now, I didn't measure it, but I think it's drawing it slower this time. I feel like this is taking longer. So, I guess what that means is if we want to pick a better way or a more efficient way of doing this that doesn't take as long, at least on this kind of calculator, I think polar was a faster way to draw this picture. If we're concerned about speed, like how fast we can do it. But we get exactly the same picture in polar and parametric. Any questions? So these are called petals, right? So this is a petal curve. And this particular petal curve has 4 petals. And this 7 shows up somewhere in this picture. Anyone have an idea where the 7 might be? Yeah?
Is it the furthest point away from the origin?
Yeah, it's basically the length of one petal. So if I make that bigger, and I take and draw the best I can like that, take that line, let me group it with something so I can rotate it now. Move that out of the way. I need some space. Let's group that. And now let me bring it back to my axes and turn it horizontal. So I can kind of measure relatively straight. So if you count, it should be 1, 2, 3, 4, 5, 6. I don't have it turned quite enough, but you get the idea. It should be about 7 units if I had drawn it perfect. Okay, I drew it a little bit off. But that's where the 7 shows up. It's the length of the petal. And this number controls something else. So the A controls the length of the petal. And what do you think the 2 controls? Yeah, it does have an effect on the width, but the easier effect to see is the, what did you say before? Number. The number of petals. So when we graph 7 sine 2 theta, we get 4 petals, 7 units long. What do you think would happen if I graph? Let's just put this here. There. Let's go back to polar because that one was easier to type in. How many petals do you think I would get if I did 7 sine 4 theta?
8.
Yeah, we'll get 8. So I just sped up, changed the step a little bit, but it still looks pretty good. So it did change the width of the petal, but more directly it gives you more petals. And then what if you did 6 theta?
Wow.
Yeah, if you did 6 theta, It's going to make each petal a little skinnier, and you should have 12 of them. And how about if I did 5 theta?
10.
5.
So only even numbers double and odd numbers are the number.
So even numbers would double the number of petals, and odd numbers would give you exactly that number.
Why?
But this is still the same length. Every one of these petals has a length of 7 units. Actually, you can probably see it really good on this one because with 5, you have a petal that lines up right on the axis. So if you count 1, 2, 3, 4, 5, 6, it's exactly 7. They don't always line up on the axis. Like if you do 4 petals, I think they could all line up on the axis. I think that's the one I did originally, right? What would happen if I typed cosine instead of sine? Yeah, it's going to rotate it a little bit. So now every one of them was just rotated by 90 degrees. So they a little bit off the axis now, but this one is right on the axis, where before it wasn't. So it rotated a little bit. It didn't rotate 90 degrees. I think it rotated, I'd have to figure it out. But you could figure out how much it rotated.
It did rotate. If you look at the one that's fully on,
Well, if it rotated 90, wouldn't this petal just end up always on an axis? But, oh, did it go counterclockwise? Yeah, maybe that's what it did. So this petal, I think is that petal. Yeah, so it did rotate 90. Yeah, and then this petal is that petal when it rotates. Yeah. All right. So, any question on that type of graph, the petal curve? All right. And the last thing we're going to look at is a spiral. So, what's it saying is going to happen in this case? How big is the radius? It's equal to the size of the angle. So, if you're at a 90 degree mark, your radius is going to be 90. If you're at 180 degrees, your radius is 180. So your radius grows exactly the same as the angle. So you can see in degrees, it gets really big. By the time you get to 360, your radius is 360 units.
Why is it called the spiral of Archimedes?
I don't know why this particular spiral is named after Archimedes. I'm not sure. Because I think there are other types of spirals, but I think the ratio of the radius to the angle in this one is named after him.
I'm going to go with that.
Sure. So let's say I want to graph one spiral, like one revolution. What would I need my theta max set to get one spiral? 360. And what's the biggest that the spiral is ever going to be as it goes from 0 to 360 on the angle? 360. So what we would want to do is let's set our window 360 to 360 in every direction. That's more than we need because the spiral is only going to be its biggest on the positive x-axis. All right? Then it's going to get bigger as it goes. Positive x-axis is the one you really need 360 on. But we'll do it everywhere just to be simple. So let's go negative 360. We need it there. We don't need quite this much, but it's okay. Now, is it going to look proportional if I set everything to 360? No, it's going to distort it, so it's not going to look exactly the way it should. I should multiply by 1.6 if I want to set a square window, but I'm not worried about that. There you go. That's one spiral. Now, what if I wanted to see 2 spirals?
Yeah. 720.
720. And then I should adjust my window. We can do all 720s. Again, it's a little overkill, but it's still going to give you a good picture. So 720, negative 720, and 720. Okay, so there's 3/4, there's 1. There's 1 1/2, 1 3/4, 2. So now you get 2 full spirals. And then we could look at what happens if we, well, let's take this picture, just save that. What do you think would happen if I went negative 720 to 0? Let's start with an easy question. How many revolutions of the spiral am I going to get?
2.
We're going to get 2. Any idea how it's going to look different from this one?
It's gonna be
You think it's going to be what?
flipped across the Y.
Flipped across the Y? Let's take a look and see. So it took the spiral and it mirror imaged it over the y-axis. So we can change these spirals to all different images. And it was just practicing with 2, 4. No, actually that's 1, 2, and 4 revolutions of a spiral. But we did it in degrees. Alright, so that's homework for tonight. On the 37 to 41, actually I think I can just change that. Let's just go like this. On the 37 to 49, those are just the odds. There's a lot of sketching on this one. Any sketches, you can always use your calculator and just copy the sketch down. I will pause the video and make sure I put a list of test topics right after you guys leave.